Yes, Aleena, am I audible?
Yes, ma'am.
Okay. Aleena, before we start with the class, I just wanted to ask, you want to complete the first book also?
Sorry, ma'am.
You want to complete the first book again?
Ma'am, like revision.
Okay. So, okay, let us complete with this first. So, anything else is there, you can let me know. Now, we have completed all the applications of it. Now, this is anomalous expansion of water. Anomalous expansion basically means the unusual property. Okay, whenever you have the term anomalous, it means unusual property, like you have anomalous properties of hydrogen also in your chemistry. So basically, this shows the relationship between the graph, the expansion of water. So two graphs are there. One is volume versus temperature, other is density versus temperature. Now, volume versus temperature, what happens? The initially temperature keeps on increasing, but volume decreases and reaches a point that is the critical temperature, which is 4 degrees Celsius. Here the density is also 1 gram per centimeter cube, and there's in the SI unit it is 1000 kg per meter cube. Then the volume versus temperature increases linearly. Then we have density versus temperature graphs. So see, temperature keeps on increasing, but there is a maximum value obtained again at this 4 degrees Celsius. So volume of water decreases from 0 to 4 degrees Celsius, but density increases, okay, in on heating from this. So this is what is important to be remembered, because volume and density, they are inversely proportional. Density is equal to mass by volume, so density is inversely proportional to volume. Clear, Aleena?
Yes, ma'am.
Okay, Aleena, I think it's just a 1 hour class, and we have, if I'll give you time to copy down every point, then we'll not be able to cover all these. These are very short things: thermal conduction, convection, radiation, CPCV. Only specific heat part is there, which I need to explain you a lot. So it's better you take the screenshot, and next class is, I think, on Tuesday only. So you have lots of time, you can write down everything. Okay.
Okay, ma'am.
How do you prefer? You tell me, how do you prefer? How to go about?
Ma'am, I want to finish before February. So, okay.
Yeah, okay. Because we can then start with thermodynamics in the next class, because this is not a very big chapter. Okay, take the screenshot.
Done, ma'am.
I'll try to do one thing, Aleena, that I'll try to send you the notes also. Okay, all these notes, like this won't be, I'll not be able to share it from this one, but the other, the notes are there. Other notes are also there. So I'll try to share this also with you, so that if the screenshots are there, you have the notes also. But one thing, Aleena, you need to write down everything, right?
Yes, ma'am.
Okay. So now understand what is the specific heat. Imagine there's a block, mass of this block is m. Now, this block's mass is m, and there are two temperatures, T1 and T2 here. The temperatures need to be increased. Okay. If I give, initially let's say the temperature is T1, ठीक है? अब इसका temperature बढ़ाना है, so क्या करेंगे? We'll provide heat to it. So what we do, we provide some heat to increase its temperature from T1 to T2. Now, what is this delta Q? It's the amount of heat provided to the body. What is the increase in temperature from T1 to T2? So change in temperature would be T2 minus T1, and m is the mass of the body. Now, delta Q, that is the heat, or that is the change in this heat, it is directly proportional to the mass, and it is also proportional to the change in temperature. दोनों ही चीज पे proportional है heat. If the mass is more, you have to provide a lot of heat. If there's a lot of gap in increasing the temperature, you need to provide that much amount of heat. So basically, heat is directly proportional to mass and change in temperature. Now, if you combine all this delta Q, this is both, this delta Q is entirely proportional to M delta T, right? Now, when you remove the proportionality sign, there's a constant that comes, which is this C, and then rest of it, that is M delta T. Now, this constant that has come, Aleena, this constant, this is basically called as the specific heat. It shows the effect of nature of material with the change in the temperature. This is what is written. Now, delta Q. Now, if I say, Aleena, what is the formula of C from here? It will be delta Q divided by M delta T. This would be the formula. It's delta Q divided by M delta T. Now, see, if I say this mass is 1 gram, okay, this change in temperature is 1 degree Celsius. So what will be left here, Aleena? You tell me. I put this as 1, I put this as 1. So what will be left?
Delta Q.
Delta Q means C is equal to delta Q. So how can you define this specific heat as? This specific heat can be defined as the amount of heat required to increase the temperature of 1 gram of body by 1 degree Celsius. Clear? Now let's come to its definition. Now you'll be able to understand. Specific heat of a solid or a liquid, it may be defined as the amount of heat required to raise the temperature of 1 kg of solid or liquid through 1 degree Celsius or 1 Kelvin. That is the specific heat capacity. So heat is directly proportional to these two things, but the constant that comes is specific heat. So it is basically a material dependent property. And now if you see from this formula, delta Q, this is joules, mass is kg, change in temperature is Kelvin. So SI unit will be joules per kg per Kelvin. CGS unit would be calorie per gram per degree Celsius. All right.
Yes, ma'am.
Take this screenshot of the specific heat capacity.
Done, ma'am.
Okay, coming to a very basic question based on this. It says that calculate the heat required to raise the temperature of 10 kg of water from 10 degrees Celsius to 50 degrees Celsius. Now, what is the formula, Aleena? Delta Q is equal to MC delta T. This is the formula. Now, you only tell me what is M given in the question? What is M given?
10.
10. Specific heat is given as 4.2 into 10 to the power 3.
3.
What is the change in temperature, Aleena?
40.
40, right? It is 50 minus 10, correct. So we'll put it this as 40, whatever answer will come, that will be the final answer. Understood? So you just have to apply MC delta T and that's it. Okay, MC delta T and all of your work will be done. In the numericals, in these questions, whatever things you have to relate it with MC delta T. So as soon as the term heat comes, heat means heat is related to that only, the change, correct? Heat is always related to the change only. So whenever you have heat means your delta Q should be there in your mind. As soon as you see delta Q, it means you're talking just about the heat. Understood? So heat and all these things, these should be very, very clear to you. Okay, don't get confused between power. Don't be confused between the other terms. Power is different. Heat is different. Okay.
Yes, ma'am.
All right. So take the screenshot of this also.
Ma'am.
Done? Oh,
Done, ma'am.
okay. Now there are various types of specific heat capacities that are present. Now look, when you are trying, see, when you just have 1 mole, you are talking about the number of moles. Okay, when you're talking about the number of moles, then the specific heat is called the molar specific heat. Means instead of that mass you are trying to increase, you are providing the temperature to increase the temperature of 1 mole. So here number of moles will be used. So the formula will be delta Q is equal to NC delta T. Okay, where N is the number of moles. So when you see the formula of specific heat, the molar specific heat, it will be delta Q by N delta T. So this is joules per moles per Kelvin. Okay. If you look at a formula, very easy question is there. Calculate the heat required to raise the temperature of 2 moles of H2 from 10 degrees Celsius to 60. So delta Q will be NC delta T. What is N given in this question, Aleena?
2.
2. C is given as 2.3 into 10 to the power 2. And the change in temperature is 60 minus 10, that is 50. 50 into 2 is 100. So it will be 2.3 into 10 to the power 4 joules. Okay. So this is about the mole. Take the screenshot of this.
Done, ma'am. Done, ma'am.
Okay. Now there is one more type of specific heat that is only for water. So when specific heat's definition and everything that we have studied is the same, but with the specific heat and the material that we're talking is just water. So we say delta Q is equal to MC delta T here, but this is the specific heat of water, CW we write, specially for water. Okay, that is specific heat of water. And one you have as the heat capacity. Heat capacity, or this is also called the thermal heat capacity. Okay, this is basically thermal heat capacity. So it's the amount of heat required to raise the temperature. Basically, Aleena, if I multiply mass into the specific heat, the term is written as S. So the formula becomes delta Q is equal to S delta T. What is this S? S is equal to M into C. Mass into specific heat capacity. So delta Q is MC delta T. Okay. So delta, this S will be the specific heat. S is equal to MC. Means the mass into specific heat, that is taken as the heat capacity, or it is written as thermal heat capacity. So formula of S will be delta Q by delta T. So that entire mass thing has gone from the formula. So that's why the formula is written as joules per Kelvin or calorie per degree Celsius. Clear?
Yes, ma'am.
Okay, take the screenshot of this page. Done?
Done, ma'am.
Okay, now it says calculate the heat required to raise the temperature of body from 10 degrees Celsius to 110 degrees Celsius. Now, by looking at the unit, this is given. If this is given where you are not seeing C, you are seeing an S, and you don't see the mass, it should immediately come to your mind that this is the, yes, exactly. So this will simply be delta Q will be equal to S into delta T. So what is delta T here, Aleena?
1000 into 100.
How 2000 into 100. Perfect. Very good. So delta Q will be S delta T, that is 2000. See, delta T will be 110 minus 10, which is 100. So it will be 2000 into 100, that is 2 into 10 to the power 5 joules. Perfect. Now, the mass of water, no, there is a term which is known as water equivalent. Water equivalent means, see, if there is water present, okay, and some amount of heat is given to increase the temperature or decrease the temperature. Now, this mass of water, okay, this mass of water that is absorbing heat or losing heat, whatever, this mass of water is called the water equivalent. This water equivalent is basically the mass. If you multiply M into CW, okay, mass into C. See, the value of CW here usually is taken as 1. The specific heat of water is taken as 1. So water equivalent is not the specific heat or something. It is actually the mass of water. Simple mass, SI unit will be kg, that mass, not the specific heat. It is simply the mass, that mass. So what we do, we multiply M into CW. So CW is 1. And what is mass? Mass is the water equivalent. So instead of writing this as M delta T, we put it as W delta T. W means your water equivalent. It's instead of the mass. This water equivalent is instead of the mass of water. This is basically the mass of water. So this should come to your mind that when you're talking about delta Q, it is the mass of water. So this will, when I am talking about the SI unit of it will also be joules per Kelvin, because mass is the delta Q by delta T. CW is already 1. And when you're talking about the CGS unit, it will be calorie per degree Celsius. That is your water equivalent. See, CW is different. CW is the water equivalent. That is 1 calorie per gram per degree Celsius. And water equivalent is the mass. This is basically the mass. Mass and specific heat, they are different. Is this clear, Aleena?
Yes, ma'am.
Okay. So there's a question. This says that calculate the heat required to raise the temperature of copper from 10 degrees Celsius to 60 degrees Celsius. Now weight is given as 10 grams. So when it says that calculate the heat required to raise the temperature of copper, see, from 10 to 60. Now weight of copper is, the W is given. This is means the mass, the water mass, the mass is given, right? The mass
Yes.
of water is mentioned. Yes, we can see the unit also. It is mentioned as grams. So simply when you're calculating heat, it will be W into delta T. The water content that is being absorbed or released, is it?
500.
Yes, correct. This is see, Aleena. This is 10 gram. Yeah, this is 60 minus 10. Perfect. Yeah, I was saying, Aleena, that whenever you're answering, remember you have to put the units also in your final
Yes.
exam. Okay. So what should be the unit here?
Joule.
No. Calories. Everything is there in CGS, degree Celsius, gram. See, if you mainly see change in temperature can be written in any ways, but when you're talking about the gram, this is specifically gram, so it would be calories. Clear?
Yes, ma'am.
Take the screenshot of you've taken for specific. This is left here.
Done, ma'am. Done, ma'am.
Okay. Now, Aleena, till the whole time when we were talking about all the specific heat capacities, there was one thing common in every question. Can you tell? Did you notice anything?
Delta T.
Yes, very good. Very good. Delta T. Delta T wasn't changing. You had mass changing, water equivalent came, specific heat capacities were different, everything was different, but delta T was the same. So one thing, have it in mind that whenever there is a change in temperature, you will be applying whatever you have studied till now. Now, coming to latent heat. This here, the first thing is that same thing, amount of heat required to change the temperature and everything. Now see, here definition is same. That change in temperature, delta T, is zero here because the temperature is constant here. The temperature is a constant temperature. So what is changing? The state of matter is changing. You have to be very careful whether it is change of matter or this. Now, delta Q is equal to ml is its formula. This is the general formula of it. Delta Q is equal to ml. So what is latent heat? Delta Q by m. So if I say mass is 1 unit, 1 gram, 1 kg, so L will be equal to delta Q only. So this says that the amount of heat required to increase the amount of heat required to change the state of matter by of 1 unit substance. Amount of heat required to change the state of matter or the state from one state to another state of unit of substance. Formula, general formula is delta Q is equal to ml. Like the formula of the specific heat capacity one is delta Q is equal to mc delta T. That is the general one. But you have different types of specific heat capacities. Na? So here also L will be different. Now see, the amount of heat required to change the unit mass of a substance completely from one state to another, means state of matter, one to another at a constant temperature, is called the latent heat of the substance. Here delta T is not there. Entire concept of delta T has vanished. So what happens here? What is the change that occurs? Like this is a very good example. Minus 10 degrees Celsius ice is existing. Now this is my starting point. Now, see, if suppose this minus 10 degrees Celsius of ice is put, now what I'm doing, I have increased the temperature and I have put it as 0 degrees Celsius. 0 degrees Celsius of ice exists. We know this is the freezing point of water. So what has happened? There is a change in temperature, but the state is same. This is solid, this is solid. This was ice, this was ice. So now the heat that is required will be calculated by mc delta T. Now, 0 degree of ice is there. I have provided more heat. So what will happen? Now, after 0 degree Celsius, the ice is converted into water at 0 degree Celsius. We have water also existing at 0 degree Celsius. The chilly, freezing water, very cold water. Thanda pani jo hota hai, that
Yes.
can exist at 0 degree, right?
Yes.
So now what is happening? Temperature is remaining constant, 0 degree, 0 degree, but from solid to liquid, it has melted. So now we cannot use this delta T formula. We are going to use delta Q is equal to ml. Ab 0 degree water hai, where you have very cold water. You've put it on stove. हीट करती हो, टेम्परेचर बढ़ जाता है, राइट? वाटर जो गर्म ठंडा पानी था, दैट बिकम्स योर वेरी वार्म वाटर, वेरी वार्म, वेरी हॉट वाटर. 100 डिग्री सेल्सियस तो बॉइलिंग पॉइंट हो जाता है. ग्रेजुअली ल्यूक वार्म होगा, ल्यूक वार्म से होते होते हॉट होगा, एंड वेरी हॉट वाटर एट दैट विल स्टार्ट बॉइलिंग 100 डिग्री सेल्सियस. बट जो water tha, that was the cold water, now is the hot water. It could be lukewarm water in between somewhere, but the state is the same. Temperature has increased, so we use delta Q is equal to mc delta T. And if you further heat it at the same temperature, it can become vapor, steam. So you will use delta Q is equal to ml. Is it clear?
Yes, ma'am.
Okay, now there are different types of latent heat also. This depends upon the process. See, if solid is melting into liquid, liquid is freezing into solid, you use the latent heat of fusion. If solid is turning into vapor, that is called sublimation. Vapor turning into solid is anti-sublimation, solidification, or deposition. And if liquid is converting into vapor, that's vaporization, and vapor into liquid is condensation. These are just the names of the processes that I have mentioned, so that if it comes in the question, you can use any of these processes. Then it says during state change, heat energy is used in changing interatomic separation. There is no change in temperature. Okay, heat can basically what it can do, heat is used to, when we're talking here, no, basically what happens, this separation is there, heat is provided, this separation, interatomic separation, this increases. This is what is saying here. That's why there is a change in the state. Like here, latent heat are of two types. It is written mostly because this is used, but there are all the other types also. Like latent heat of fusion. Fusion means solid turning, when you have a solid turning into liquid. Like the melting process, melting is basically fusion. Okay, this is basically melting. So solid turning into liquid is the latent heat of fusion. So you will use the formula delta Q is equal to MLF. This will be mentioned in the question. Similarly, latent heat of vaporization, liquid into gaseous state. So delta Q is equal to M into L. This is the formula. SA you will have sublimation also, delta Q is equal to M into LS. So L will be Q by M. Q is the heat, so SI unit is joules. M is the mass, so SI unit is kg. So what will be the SI unit of latent heat? Joules per kg or calorie per gram. Have you understood this?
Yes, ma'am.
Okay, take the screenshots of this.
Done, ma'am. Done, ma'am. Done, ma'am.
Okay, now the concept of calorimetry, Aleena. Oh, before that, yes, questions also. See, it says calculate the heat required to melt 10 kg of ice. So see, 0 degree of ice is getting converted to 0 degree of water. So delta Q will be simply M into LF. So 10 into LF is given to you in the question, 3.5.
3.3 into 10 raised power 5.
So final answer will be 3.3 into 10 to the power 6 joules. Similarly, this is vaporize 100 kg of water into this. Easy?
Yes, ma'am.
M into LP. 22.6 into 10 to the power 5 into,
100.
yes, 100. Correct. So this will be 22.6 into 10 to the power 7 joules. Now, Aleena, there's a graph also. There's a graph that can come. So if the question is in the graphical form like this, so understand everything. Here the temperature is given and here the heat is given on x-axis. So minus that same example, the same example I have taken, but if it comes in the form of graph, so extract data according to your needs. Like minus 10 degrees Celsius of ice. Now the temperature is remaining the same. State has changed. So see, 0 degree. Now see, sorry, the temperature has changed here. So we have the graph of temperature changing. Look, this is the graph of temperature. At every point it is changing. State change, no change in temperature. Now temperature has increased 0 degree. Again, it is at 0 degree, so no change in temperature. So you can use all these formula for the calculation. Is it clear?
Yes, ma'am.
Okay, before I start with this calorimetry part, just take the screenshot of these two.
Done, ma'am.
Okay, Aleena. Now let us come to the calorimetry part. Basically, what is calorimetry? So calorimetry, no? Uh, just a minute, just a minute. Wait. Yes, Alina. So, see, basically, the calorimetry is just a method to find out how much heat has been exchanged. So, the principle is the law of heat exchange. Law of heat exchange basically means whatever heat has been lost is equal to heat gained. Now, one object will lose the heat, other will gain that heat. So how is the calorimeter constructed? There is a basically wooden jacket, this orange part which I have encircled. So basically this wooden part shows that this is an insulator. And inside there was a copper vessel. Okay, inside there was a copper vessel. So copper is metallic. Now the liquid was filled and thermometer was there to measure the temperature, and there's this stirrer to just move the liquid. So suppose aluminium is filled here, so whatever heat will be lost by the aluminium will be gained by the copper vessel, and that amount will be measured in the temperature. So this is how the calorimeter works. Now there's a question. This says that a sphere of aluminium of 0.047 kg is placed for sufficient time in a vessel containing boiling water. So that sphere is at 100 degrees Celsius. It is then transferred to 0.14 kg copper calorimeter containing 0.25 kg of water at 20 degrees Celsius. Temperature of water rises and attains a steady state at 23 degrees Celsius. You have to find the specific heat of aluminium. Basically, what is happening? See, this is the container. Okay, there is aluminium. Okay, and what is this doing? This is a sphere of aluminium. Okay, this is the mass. This is placed in the vessel containing boiling water. So here the temperature, what is the temperature here? It is 0 degree Celsius. Okay, initially the temperature is 23 degrees Celsius, and this temperature increases up to 100 degrees Celsius. This is what it is doing. Then it says it is then transferred to copper calorimeter. This is then transferred to a copper calorimeter. Let's say this is the copper calorimeter. Okay. And then what is happening? So that the sphere is at 100 degree. Yeah. So now the temperature is 100. The final, initially it was at 23 degrees Celsius. Now this is that increased temperature, 100 degrees Celsius. Okay. It has water also. So whatever heat will be lost, what is happening? Heat is being lost because temperature is rising, right? The temperature is rising and this has water is attaining a steady state of 23 degrees Celsius. We have to tell the specific heat of the aluminium. So what is happening here basically, Aleena? Aluminium is losing some amount of heat. Now, aluminium, when it is put here, it is losing some heat that is gained by copper and it is gained by the water. Okay, so basically we can say heat lost by aluminium will be heat gained by copper plus the water. Now, MC delta T for aluminium, because there's a change in heat, MC delta T for the copper, MC delta T for water. So how will we put mass of aluminium, specific heat of aluminium into change in temperature? Final temperature minus initial temperature of aluminium is equal to, what will be the heat gained by copper? Mass of copper, specific heat of copper, final temperature of copper minus initial temperature of copper, plus mass of water, specific heat of water, final temperature of water minus initial temperature. Now see, all the values are given in the question except for C aluminium, just it is missing. See, mass of aluminium is given, C aluminium is missing, which you have to calculate. Initial temperature, see, final temperature it is saying no, 23 degree Celsius पे steady state हो जाता है. So 23 degree Celsius will be common for all. Aluminium भी, copper भी, water भी, because when the temperature was different, see it said ना, it इसका 23 हो गया 100 हो जाता है, and ये 100 से इसमें पुट होता है ना, 100 डिग्री सेल्सियस से. अब क्या होता है, जब इसने हीट लूज करी तो इसका 23 डिग्री सेल्सियस हो गया, वाटर का 23 डिग्री सेल्सियस हो गया, कॉपर का 23 डिग्री सेल्सियस हो गया. कैलोरीमीटर का प्रिंसिपल यही है, जब तक टेम्परेचर सारे सेम नहीं होंगे, द बॉडी विल कंटिन्यू टू लूज द हीट. तो इसीलिए you have all the final temperatures equal to 23 degrees Celsius. Now temperature initial is 100 degree, coppers and water is given as 20 degree. You can put it in the formula and calculate. Is this clear to you, Aleena? Have you understood this calorimetry?
Yes, ma'am.
Okay, take the screenshot of this.
Done, ma'am. Done, ma'am.
See, specific heat we have studied. Now, if the volume is kept constant, so the specific heat is referred to as the CV. CV will be used. So how will you say? Delta Q is equal to M CV delta T. So your CV will be equal to delta Q by M delta T. This is the specific heat at constant volume. This will come in thermodynamics also. Be very careful with this. This is very important. So it is defined as the amount of heat required to raise the temperature of 1 gram of the gas through 1 degree Celsius at constant volume. And what is CP? Same thing. Pressure is constant. So CP. So delta Q is equal to M CP delta T. So CP is equal to delta Q by M delta T. Same thing. CP. We will be using this again in thermodynamics, so please revise this properly. Okay, this is clear. Specific heat at constant volume and at constant pressure. Clear? Take
Yes,
this.
ma'am.
Take the screenshot of this too.
Done, ma'am.
Now the concept of thermal conductivity. What is conduction? So in conduction, what happens is that there is transfer of heat. Suppose this is the edge of a rod. This is the other end of the rod. Okay, there are molecules present. Okay, these are the molecules which are present in, this is made up of these molecules like this. So about the atoms and molecules and all, you will be studying properly in your class 12th. You have the whole unit from them. So now these molecules aren't moving. This is, let's say I have put heat here. So all these are now becoming, all these molecules are now becoming hot. Okay. Because of the heat, all these molecules, they are becoming hot now. So heat, they'll vibrate. Okay. They will vibrate and they will transfer the heat to these. Now they will have the heat. So they will vibrate and transfer the heat to here like this. So like this, the entire heat will reach to the cold side. So from hot to cold, there is transfer of heat, but molecules are not moving. It's just the vibration that is causing. So conduction, it is the process by which the heat flows from the hot end to the cold end of the solid body without there being any net movement of the particles. Remember, this is a classic sign for conduction to be remembered, without there being any net movement of the particles of the body. Now, what is thermal conductivity? Thermal conductivity is the measurement, how much amount of heat has flown through an object. Okay, when you're talking about thermal conductivity, this will tell you how much the heat has flown. Okay, so whenever you have here the concept of thermal conductivity, be very careful with it that it is material dependent. So is the materials heat changing or not? All right. So when we're talking about this, delta Q is equal to K, change in area, change in temperature by the thickness of the material. So K, okay, K, A, delta T, okay, and multiply. This is actually delta Q by delta small t. So what is small t? Small t is the time, change in time. So delta Q can also be written as, this is the coefficient of thermal conductivity. Okay, this is the coefficient of thermal conductivity. This will define. What is A? A is the area. Delta T is the change in temperature. And delta dx is the thickness of the material. So delta Q can be written as KAT delta T by dx also. Delta Q is the heat. So remember, K is what? It's the thermal coefficient. Thermal conductivity, is coefficient of thermal conductivity. Clear, Aleena?
Yes, ma'am.
Anything you want to ask?
No, ma'am.
Okay. So this is what is your thermal conductivity, coefficient of thermal conductivity. So when you put everything unit, 1 meter, 1 degree Celsius, time as 1 second. Okay. So what will happen? Thickness 1, area 1 meter square, time 1 second, change in temperature 1 degree Celsius, K will be equal to the Q. So it is defined as the amount of heat that is flowing for 1 second between the opposite faces of a cube of each side 1 meter, and the faces being kept at a temperature difference of 1 degree Celsius or 1 Kelvin. Now, what is temperature gradient? Temperature gradient means how much temperature is changing with respect to position. So delta T over delta X is called the temperature gradient. Gradient term means only something changing with respect to position. Okay. There is these are some applications of thermal conductivity, like cooking utensils are made of metals, but always handles are made up of bad conductors because conduction occurs. That's why the heat flows in metals. Otherwise, how will you be able to hold the things? Because they will also become hot. When hot water is poured in a beaker of thick glass beaker can break because of the heat, excess heat. An ice box is a double walled box because see, it is doubly walled because the heat can come and it can melt the ice, so it is doubly insulated. And coming to this question, this says calculate the rate of heat through a glass window. So area is there, thickness is given, temperature is there, change in temperature can be calculated, and this. So rate of heat loss is there, Aleena. So you need not multiply time there. delta Q over delta T, you see. Rate of heat loss means how much heat is getting lost in some time, losing of heat for a period of time. That is Ka dt over dx. So K is 2.2 into 10 to the power minus 3. Area is 1000 centimeter square. So 10 to the power minus 4. No, everything is there in CGS only, no? So let's put this also in CGS. Okay, so 1000, this into 1000 into change in temperature. 37 minus 5. So that will become 42. Divided by, thickness is not given. Yeah, 0.4 centimeters, yes. So 1000 will be cancelled. This can be solved. Whatever will be the answer will be calorie per second because this is in CGS. Am I clear, Aleena?
Yes, ma'am.
Formula you have understood. What is this formula? What is K?
K is constant.
Constant coefficient of thermal conductivity. A is
Area.
dt. What is this 42? Temperature change, no? 37 minus 5. What I was doing?
Yes, ma'am.
Yes, temperature change. What is dx?
Dx is thickness.
Thickness, right. Take the screenshot of this also.
Done, ma'am. Done, ma'am. Done, ma'am.
Okay, what is this convection? Convection is very easy. Now here the movement of particles. Suppose this is the hotter end, means here we have put the flame. So this is the hot particle now. This will move from this end to this other end. So hot particle will reach towards the colder end like this. That is what is convection. So the process by which heat is transmitted across a substance from one point to another due to actual bodily movement of the heated particles of the substance is called convection, like heating of rooms, cooling of transformers. And what is radiation? Without any medium, when there is a transfer of heat, because which travels with a straight line like the speed of light, it is called the radiation. Like the sun rays, when the sun rays are coming, that is radiation, because the sun rays travel with the speed of light. The ultraviolet rays, okay, that are coming, infrared radiation, they travel with the speed of light. So you have an electromagnetic spectrum. This electromagnetic spectrum and electromagnetic waves detail is there in your class 12, so you need not know about that. Now, what is radiation? The transfer of heat from one place to another in a straight line with the speed of light without heating the intervening medium is called radiation. So transfer of heat without heating intervening medium. Best example is your EM waves, electromagnetic waves, like your infrared waves, whose wavelength is this. You need not remember this. Just remember some examples. Now, every body having temperature more than 0 Kelvin, this is the absolute temperature, emits thermal radiation. So radiations are taken out, and intensity of these radiations is inversely proportional to square of the distance. Means if the distance is more, the intensity will be very less. And if the distance is very close, like if you have the light very close, you'll see high intensity light radiated. So that is obvious. Now, there are few processes that occur. Thermal energy when it is incident on the surface. First, when the light ray is struck, it can bounce back. This process is reflection. When amount of light is absorbed by the body, it is called absorption. And when some amount of amount of light is given to the substance, it is called transmission. So reflection and transmission, these are there in your class 12th. Reflection in the form of refraction, there you will be doing this. Absorption, this is there. So how is the absorption done? Remember one thing, that a perfect black body has 100% absorption. This is one thing that you should remember, has 100% absorption. Okay, so there's a formula. Whatever is the radiated light, okay, the thermal radiation reflected divided by the thermal radiation that is incident gives you reflectance. So it is represented as small r, written as r by q. R is the thermal radiation reflected. Delta q, this q is the thermal radiation absorbed. Oh, sorry, that is incident, this one. See, this divided by this incident. Whatever is absorbed divided by this is absorptance. Whatever is transmitted by, which is what was incident, is transmittance. So this is the incident ray. This is fixed. Incident ray is fixed here. This is the incident one. So reflected ray by incident is the reflectance. Absorbed amount of heat by the incident is absorptance. Transmitted by the incidence is transmittance. That is what is written here, absorptance, transmittance. And the formula of small r plus a plus t is always equal to 1. So you can say r by q, that is ray reflected by incident, ray absorbed by incident, ray transmitted by incident is always equal to 1. This just comes in the theoretical part. You don't have numericals from this, but you should know. Now, one is monochromatic emissive power. What is this monochromatic emissive power? This basically tells about the intensity. Okay, the wavelength emitted per second per unit area means wavelength. Whatever is the wavelength that is emitted, radiant energy of that wavelength emitted. So basically, it's like your intensity. So if I say the formula of this, the intensity will actually be equal to energy per unit area per unit time. That is monochromatic when single wavelength is there. And if you have, if I say whatever is the total, you have lots of waves, and whatever is the total radiation per unit area per unit second, that is the emissive power. Power is basically emissive power. This is given as total. This is also the same, but this comprises of all the waves. So again, energy by area by time. What is the difference between these two, Aleena? This is for a single wavelength, monochromatic. And emissive power is for all the waves, whatever waves are there. And what is this emissivity? It's the ratio of these two. So basically, E by capital E. E is the emissive power of any body, and capital E is the emissive power of a black body. So when you take their ratio, it is given as emissivity. So emissive power is ratio.
Like E. This is like 3 emissivity.
The symbol is called epsilon. This will come a lot in your class 12th. Epsilon symbol. This is just a Greek symbol like alpha, beta we have. No? So
Okay,
that
ma'am.
is emittivity. So this, which looks like in E, this is the symbol is called epsilon. So here it represents emissivity. Means ratio of emissive powers only. But emissive power of any body compared with that of black body, because black body का तो 100% absorptance है, 100% radiation होगा, perfectly black body will be absorbing all the light ray. That's why we compare for any body with the black body. Okay, clear?
Yes, ma'am.
Okay, take the screenshots quickly.
Done, ma'am. Done, ma'am. Done, ma'am. Done, ma'am.